So here we have different functions defined by integral, and we are trying to differentiate. The first thing that you may think is that, well, let's evaluate that integral and then differentiate. Some of these integrals are not easy to evaluate. For example, the first one, no one on earth has a good basic function, the function that you have been working in the calculus to evaluate that function, that integral. But you actually don't need to evaluate. This is fundamental theorem of calculus part 1. It says that integral of a continuous function from a constant to x with respect to x is just that integrand evaluated at x. That's simple. The second one, yes, okay. So I want to kind of use the fundamental theorem of calculus, but the first thing you have to note here is that this whole thing, I don't know what is that. You can go ahead, evaluate that, use whatever tools you know, but at the end is going to be a number, a constant, which has no x in it. You already integrated, you get just one number, yes? Because there is no variable in the limits. Derivative of constant, no matter where that constant coming from, is it the value of some definite integral, or it's given, or derivative of constant is always equal to 0. Okay. The next example, oh, there is a bad thing happening here. So this, the integral has different things here. Okay. So here what you have, so we are trying to differentiate an integral. The upper limit has the variable of differentiation. That is where you know that you have to use fundamental theorem of calculus part 1. How do we use that one? Okay, so if I know that if this was integral 0 to t of x cosine x dx, fundamental theorem of calculus part 1 would say that, okay, just plug in that t in there. So t cosine t. But now, instead of t, I have sine t. It means that this function that you had here is composed with sine t. Sine t is inner function, and this is outer function. So the chain rule says that the derivative of inner function times the derivative of outer function, which already we found, but instead of the variable, plug in the inner function. So inner function is sine t. I'm plugging sine t for t here. So it will be sine t cosine of sine t. So derivative of sine t itself is cosine t, and that is sine t cosine of sine t. And the last example here, with the similar arguments there, you can handle this thing, but first you have to see that there are two integrals here. I can go from 0 to ln x, u for e to the power u minus u cubed ln u du, plus e to the power x to 0 of u to the power 4 e to the power u minus u3 ln u du. And then switch the upper and lower limit of this guy, but that will introduce a negative sign. The reason that I am doing this is just to generate a situation like the example 3, and then you can go ahead and do the same steps as before. Derivative of this guy, ln x prime, times the inner function, the function, the integrand, but evaluated at ln x. So it will be ln x to the power 4 e to the power ln x minus ln x to the power 3 ln of ln x. So that is the derivative of first part minus here derivative of e to the power x, evaluate, oh, this must be here. Then evaluate the integrand at that guy. So it will be e to the power x to the power 4 e to the power x minus e to the power x to the power 3 ln of e to the power x. That's it. So we have now almost a formula, but the only thing we need to know here is that derivative of ln x is 1 over x, ln x to the power 4, e to the power ln x is x minus ln x to the power 3 ln of x. That's the first part minus derivative of e to the power x is e to the power x. E to the power x to the power 4 is e to the power 4x. This is e to the power x minus e to the power 3x. Ln of ex is just x. And this way, we have found the derivative of some functions defined by some integrals using fundamental theorem of calculus part 1.